Selamat pagi, selamat datang dalam para hadirin pada kesempatan siswa guest lecture hari ini. Perkenalkan, saya Herlina Abidupulu, menjadi MC pada acara hari ini. Yang pertama, kepada Kepala Departemen Matematika Unpad, Ibu Dr. Emma Tania. Yang terhormat Kepala Departemen Geofisika, Bapak Rozan Rosandi. Yang terhormat Kak Prodi S1 dan S2 Matematika FMIPA Unpad. Yang terhormat para Ketua Fakultas, sini telah hadir Prof. Dr. Sudrajat Setian dan Prof. Dr. Budi Nurani. Kepada yang terhormat para guru besar Departemen Matematika dan tidak lupa yang kami hormati Bapak Ibu hadirin yang kami muliakan. Marilah kita bersama-sama berdoa untuk mulai acara ini menurut agama dan kepercayaan masing-masing. Berdoa dimulai. Berdoa selesai. Selanjutnya, marilah kita dengarkan laporan dari Ketua Panitia, yaitu Ibu Dr. Dian Hairani yang akan menyampaikan laporannya kepada Ibu Dr. Dian Hairani. Assalamualaikum warahmatullahi wabarakatuh. Untuk bahagia kita semua bisa hadir di ruangan ini bersama untuk mengenalkan guest lecture yang pertama untuk program studi S2 dan S3 matematika, yang mana kami maksudkan guest lecture ini juga untuk mengawali masa perkuliahan di semester ganjil 2022 dan 2023. Hari ini juga kita sangat berbahagia karena kedatangan tamu yang sekaligus menjadi narasumber kami, yaitu dari Kaiserslautern University, Jerman, ya, Pak Rozan Rosandi, M.Sc. Dalam hal ini nanti Pak Rozan akan menyampaikan kuliah singkat ya mengenai Isogeometric optimization of Tensor. Sebelumnya kami juga selaku Pak Koni dan Ketua Penyelenggara kegiatan ini ingin menyampaikan bahwa kegiatan hibrid ini terselenggara dengan baik ya atas dukungan dari Departemen Matematika FMIPA, juga Departemen Geofisika FMIPA, dan juga dari dukungan dari fakultas. Kami sampaikan bahwa peserta yang mengikuti kegiatan ini total yang mendaftar di link yang telah kami sampaikan itu sekitar 58 orang, dengan jumlah 18 orang yang menyatakan bersedia hadir secara umum. Jadi kalau misalnya memang hadir semua, seharusnya yang mengikuti kegiatan ini secara daring ada sekitar 40 orang. Kita tunggu dulu ya, nanti biasanya masuk satu demi satu. Nah, kemudian secara geografis ini juga alhamdulillah bisa kami sampaikan bahwa kegiatan ini diikuti oleh peserta yang tersebar ya, dari seluruh Indonesia. Jadi ada beberapa wakil dari Indonesia Timur yang juga turut mengikuti kegiatan ini, dari Indonesia bagian barat, dari Pulau Sumatera, Jawa, Kalimantan, dan Sumatera. Ini di catatan kami ada tanyakan domisili biasanya untuk melihat representasi. Dan memang untuk kegiatan ini sebagian besar pesertanya adalah dosen peneliti dan para mahasiswa S1, S2, dan S3. Besar harapan kami, kegiatan ini dapat memberikan manfaat yang sangat besar untuk pengembangan keilmuan di Departemen Matematika dan juga prodi S1, S2, S3 matematika kami. Selain itu juga menjalin hubungan kerjasama ke depan, barangkali kita akan jajaki kegiatan lainnya ya dengan Departemen Matematika Tehnische Universitat Kaiserslautern Jerman. Mudah-mudahan nanti Pak Rozan bisa membantu kami juga untuk bisa menggunakan kerjasama sekarang ini. Barangkali demikian pengumuman dari kami. Terima kasih. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Jadi terima kasih kepada Bu Dr. kami laporan ini. Selanjutnya kita persilakan kepada Ibu Dr. Emma Tania untuk memberikan membuka acara.
Assalamualaikum warahmatullahi wabarakatuh. Saya nanti telah belajar kemudian juga Profesor Untitled serta para jurusan yang ada di Universitas dan juga Unpad. Kemudian juga Lantai dulu kita ada berkenan dulu dari Novi juga tentunya pada ketua panitia yang sekarang yang telah mendengarkan dengan baik serta Bapak Ibu Kapolri sambil dan kita para hadirin semua juga tidak lupa tentunya ucapan selamat datang yang disampaikan kepada Kang Rozan Rosandi M.Sc sebagai narasumber kita hari ini. Ya, alhamdulillah Departemen kita sangat bergembira gitu dapat menyelenggarakan kuliah tamu yang akan diberikan oleh Kang Rozan Rosandi dengan tema Isogeometric Optimization of Tensor. Ya, perlu kami sampaikan bahwa kegiatan ini merupakan rangkaian dari kegiatan KESA 2022 di Departemen Matematika yang bekerjasama dengan program studi S2 S3 Matematika. Ya, KESA ini merupakan suatu program penguatan internasional di Unpad yang dicanangkan oleh Universitas guna tercapainya Universitas Unpad sebagai universitas top 500 dunia. Ini merupakan salah satu untuk mengarah ke sana. Sehingga besar harapan kami dengan adanya kegiatan ini juga dapat berkembang lebih lanjut, menambah wawasan dan juga tentunya ini bisa menjadi titik awal untuk kolaborasi yang lebih lanjut. Jadi dalam kesempatan ini kami ucapkan terima kasih kepada Kang Rozan Rosandi. Dan untuk mengawal ini maka secara resmi dengan diucapkan Bismillahirrahmanirrahim. Kuliah tamu yang akan diberikan oleh Bapak Rozan Rosandi M.Sc dari Universitas Kaiserslautern Jerman yang bertemakan Isogeometric Optimization of Tensor resmi dibuka. Selamat terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Baik, terima kasih kepada Ibu Presiden. Semuanya, kita akan masuk ke materi sama, yaitu pemaparan yang akan disampaikan oleh pembicara kita yang luar biasa, Bapak Rozan Rosandi M.Sc, dan akan dimoderatori oleh Ibu Dr. M.R. Pada itu dia.
Terima kasih. Baik, Bapak dan Ibu, barangkali kita akan mulai kegiatan ini, namun sebelumnya mohon respon dari Bapak Ibu yang ada di rumah, apakah suara kami terdengar dengan jelas? Bu Ici?
Kurang jelas, Bu. Kurang
Jelas?
jelas.
Oh, kurang jelas. Sebentar, saya akan coba besarkan mungkin volume. Oke, bagaimana sekarang, Bu? Apakah sudah terdengar jelas?
Ya, lumayan, Bu.
Oke, makanya nanti kita harus coba yang lebih kencang ya. Jelas ya? Oke, terima kasih responnya. Baik, Bapak dan Ibu, kita akan memulai kuliah tamu ini. Mohon izin saya menyampaikan beberapa hal mengenai narasumber kita hari ini. Kami sampaikan bahwa narasumber kita adalah Rozan Rosandi. Beliau adalah research assistant and PhD student in mathematics di Tehnische Universitat Kaiserslautern. Saat ini beliau sedang menempuh studi S3 ya, di Kaiserslautern, dan pendidikan yang telah ditempuh Bachelor Science in Mathematics with subsidiary subject thesis di Technische Universitat Kaiserslautern, dan juga Master of Science in Industrial Mathematics dan juga di Technische Universitat Kaiserslautern. Research interest yang didalami oleh Rozan ini adalah mathematical modeling and scientific computing, kemudian numerical analysis of partial differential equation, mathematical theory of thin elastic cell, PDA constraint shape optimization, Riemannian geometri dan isogeometric analysis. Kemudian beliau juga memiliki beberapa experience dalam hal mengajar, antara lain mengenai higher mathematics, ya, 1, 3, and 4 for beginner student, fundamental of mathematics analysis, introduction to vector analysis, ordinary differential equation, introduction to numerical method, and serta numerical method for partial differential equation. Dalam hal ini adalah elliptic and parabolic PDE. Ya. Jadi kita hari ini berkesempatan untuk berkenalan, gitu ya, sekaligus juga akan mendengarkan riset pembuatan ini apa. Mohon para mahasiswa bisa menyimak dengan baik dan mungkin bisa juga mengajukan pertanyaan nanti di depan, sehingga kita bisa memperoleh insight dari riset ini, utamanya mungkin untuk pengembangan yang lainnya, ya. Termasuk optimisasi. Saya juga backgroundnya optimisasi, ada juga dari riset operasi dan optimisasi. Sehingga judul ini untuk saya sangat menarik karena biasanya kami melaksanakan riset operasi dan optimisasi banyak di industri yang berkaitan dengan decision science seperti ini. Kali ini akan jauh lebih berkembang lagi, gitu ya. Apalagi di sini mergernya dengan numerical method, ya, PDE dan lain-lain. Ya. Nah, untuk waktu kami serahkan sepenuhnya kepada Kang Rozan. Santai saja, begitu ya, silakan. Dan barangkali mohon izin, ini Kang Rozan ingin menyampaikan kuliahnya dalam bahasa Inggris, ya. Karena Kang Teteh semua ini mahasiswa S2 juga sudah punya tekad KBI yang oke, jadi tidak masalah sama bahasa Inggris, ya. Maka silakan Kang Rozan untuk langsung saja untuk bisa menyampaikan presentasi.
Ya, saya buka ya Masnya supaya kedengaran suaranya.
Boleh.
Oke, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Ya, ya, seperti katakan sebelumnya, saya sampaikan dalam bahasa Inggris karena banyak istilah-istilah juga yang maaf saya kurang tahu translasi bahasa Indonesia apa, jadi mungkin supaya lebih lancar dalam bahasa Inggris. Oke, good. Then let's start. Again, my name is Rozan Rosandi, and I'm a PhD student at the University of Kaiserslautern in the Differential Algebraic Systems and Numerical Mathematics. My supervisor is Professor Dr. Björn Simeon, and today I would like to talk about the topic of my research and also maybe teach you a little bit about the methods and tools I use for it, namely the isogeometric shape optimization of thin cells. Okay, so I will explain briefly what isogeometric means and also what thin cells are. But before we come to that, maybe a short outline of this talk. So I would like to talk about the background and motivation for my research first. Then I will talk about the optimization framework I use to do shape optimization. So the optimization of shapes. And then I will also talk about isogeometric analysis and what is meant by it. Next, if we have more time than intended, I will also talk a little bit about the model I use to describe thin cells. In the end, there are some numerical examples and also a short summary and outlook of this presentation. Okay. If there are any questions, you can interrupt me. You can also ask your questions in Indonesian if you want to. Then I will also answer to your question. Good. Then background and motivation. First of all, maybe you are asking what are cells? So what is meant by a cell structure and where do they occur? So simply said, shell is a three-dimensional solid. Whose thickness in one direction or in one dimension is considerably small relative to the other two dimensions. So like the picture here on the right. And the thing about cells is we can reduce the physical model to a two-dimensional one by considering only the kinematics and dynamics on some reference surface, for example, the mid-surface of this shell here. And there are various engineering applications of cells, for example, in vehicle engineering, in automotive industry, in aerospace industry, or in naval engineering. For example, the body of a car is made out of cells, and also the hull or maybe the airfoil of an airplane, or also the hull of a ship or a submarine is made up of shells. But there are also applications in architectural engineering. For example, here on the right, you see the Transworld Airlines Flight Center at the John F. Kennedy International Airport in New York. And this is a pioneering example of thin cell construction. Yeah. So yeah, thin cells also occur in architectural engineering. But there are also applications in places where you do not expect, maybe in biomedical engineering. For example, blood vessels can be, or the valve of hearts, or prosthetics can also be modeled as thin cells. But also in everyday objects like the casing of foods, or electronic casing, food containers, or maybe I can just put it out, yeah, electronic casing like this part, my mouse, is, can also be considered as a thin cell structure. Okay, so the theory of cells has been really, I mean, the theory has been dealt with for many years, and there are a lot of references, a lot of papers regarding the modeling and the simulation of cells. To not get lost in the amount of paper that exists, I will focus on one main reference for cells, namely this following entry of the Encyclopedia of Computational Mechanics, the models and finite elements for thin wall structures by Bischoff et al. In 2004. Good. So, and what am I interested in? I'm interested in the optimal safe design of cell structures. Why? Well, structural optimization has great potential in the construction industry, and nowadays automated digital prototyping using, well, yeah, computational software has gained more industrial relevance because of because of the rise in computational power, and also additive manufacturing or 3D printing allows now the construction of complex geometries, which was not available before. And my research objective is to develop computational methods for the shape optimization of cell structures using something called isogeometric finite element analysis. So maybe first of all, I'm not sure about your background. If you want to, you can raise your hand. Who is familiar with the theory of partial differential equations and finite element analysis? So is there anyone who is working in this field? Okay, it seems that no one is in this field, so maybe I have to explain a little bit more about what is meant by finite element analysis. So we are dealing with partial differential equation, and finite element analysis can be seen as a computational approach to solve PDEs numerically, to solve partial differential equations numerically. And usually what we do is we use so-called shape functions to approximate the solution to the PDE. And in standard finite element analysis, those shape functions are usually called nodal basis functions. So I will tell you more about it. But now what is special about our isogeometric is instead of those, if we have a PDE, then we have a domain. And we usually discretize this domain into triangles or quads or polyhedron. And then on these polyhedron, we approximate the solution to the PDE with polynomials, usually in the finite element analysis. Now in the isogeometric analysis, so this is a different kind of finite element analysis, we do not subdivide the domain into triangles, but we use so-called NURBS and B-spline functions. Maybe you have heard of it from the numerical methods to describe the geometry or the domain of the PDE. And then we use the same shape functions used to describe the geometry to approximate the solution to the PDE. So that's the basic idea of what isogeometric finite element analysis is, or short IGA. Okay, and a lot of work has already been done regarding shape optimization and also the simulation of cells using IGA. For example, by Joseph Kindle from the Technical University of Munich, in 2011, and also regarding the isogeometric shape optimization, there's the work by Daniela Puseder, her PhD thesis in 2015. Daniela Puseder was also a PhD student of Bernd Simeon, and this is also the connection why I also deal with this problem. Okay, good. So the focus of this talk, of course, this is a fairly large topic, but today I would like to focus on the so-called Riemannian framework for shape optimization, which is a fairly new and a modern view on shape optimization, and also the connection of it with isogeometric analysis. Especially, I would also like to talk about one specific problem, namely the compliance minimization or of shell structures under a static load and fixed area constraint. Okay, so I will assume a little bit of knowledge in nonlinear optimization with partial differential equations, and also maybe computational mechanics a little bit, and also some differential geometry. So that will be the background that you need to follow this lecture. Good. So let's start with the optimization framework. So how can we pose a general shape optimization problem, or more specifically PDE or partial differential equation constrained shape optimization problem? So in general, we want to minimize an objective function here called J, which depends on some shape or design variable omega. Yeah, I will show it with the mouse, and some state variable U, which should be the solution to some partial differential equation. Yeah, so subject to the constraint that the so-called state equation, which again describes the partial differential equation, should be fulfilled. Okay. Now, omega again is the shape variable, and it is an element of the so-called set of admissible shapes. Usually, these are subsets of some ambient space, for example, the plane R2, or maybe the space R3. And U is a family of function spaces for the solutions to the PDE posed on the domain omega. Now, if some of you are familiar with optimal control problems, yeah, so the theory of optimization with partial differential equations, then this might look fairly similar. The difference in shape optimization is that this state space U is now dependent on the shape omega. So usually in optimal control problems, this space here do not depend on the domain omega, but now in shape optimization, it depends also on the design variable omega. So this introduced difficulty also in shape optimization. So some examples, maybe to get a feeling, maybe we want to optimize a two-dimensional airfoil. So here you see the profile of a two-dimensional airfoil, and the objective might be to maximize the lift while keeping the drag of the airfoil low. Or we could also minimize the drag while keeping the lift while keeping the lift bounded to some prescribed value. That would be a shape optimization problem. And here, because we want to simulate the airflow around the airfoil, the domain omega would be just the ambient space surrounding the airfoil. Yeah, portrayed in gray. Another example, which is closer to what I would like to present today, is the optimization of a wrench. Yeah, you see here a wrench, and here we have an elastic solid. And again, this can also be modeled as a thin cell, because if you look at the wrench, if you flip it, then you see that this is also a thin cell structure. And here, what we would like to minimize, for example, is the so-called compliance. Compliance corresponds to the inverse of the stiffness. So minimizing the compliance corresponds to maximizing its stiffness, thus increasing its structural integrity. Okay. We can also impose some fixed boundary condition on the left, impose some mechanical load, or also some geometric constraints. Okay. Any questions up to here about the problem formulation? No? Good. So, and yeah, there are different ways to formulate this mathematically. So in general, here S is the set of admissible shapes, And in general, these are this is a subset of the power set of maybe the plane R2. Yeah? And as you may know, the power set of the plane is already an incomprehensibly large set, in the sense that it contains every imaginable binary image. It contains the full text of every book that has been written. It contains the full text of every book that will be written, and then that also will never be written. So in general, this set of shapes is quite a large space, and we want to do analysis on it. We want to restrict it to a smaller, fairly smaller set. And there are many ways to do it. There is something called perturbation of identity, or the velocity method for shape optimization. What I would like to present today is the so-called Riemannian framework for shape optimization. What does it mean? Well, we consider this set of admissible set as a so-called Riemannian manifold. So maybe also a question: who has heard of a Riemannian manifold before, or a manifold in general? Okay, so a manifold, as you may know, is a space, a topological space, which is only locally Euclidean. Yeah, in the sense that usually we work with R2 or R3. Those are linear spaces, linear vector spaces. But Riemannian manifolds are not necessarily linear. But if you zoom in close enough, so locally it behaves like a Euclidean space. Yeah. So this is not a precise definition. So if you would like to, it should be a second countable Hausdorff topological space with some such that each point has a neighborhood homeomorphic to a subset of the Euclidean space. But informally, you can just think of it as a space which is locally linear, and at each tangent space you have a family, you have an inner product or a family of inner product called the Riemannian metric, which and with this metric you can introduce a notion of angles and also distances on the manifold. Okay, and a classical example of a Riemannian manifold would be the surface of a sphere, yeah, or maybe the globe or the Earth can be seen as a if we model it as a sphere, we can see it as a Riemannian manifold, in the sense that globally this is not linear. Yeah? This is not a linear space, but if we zoom in close enough, well, it looks linear. Yeah. So we are standing here on the Earth and it looks linear, but globally, if we just go in one direction, we will return to our original position, because this is not a linear space. Okay, and yeah. At every point of the manifold, there's also something called the tangent space, yeah, which is now an approximation of the space at this point, and this is denoted by TPS. And yeah, so what I would like to talk today is we would like to generalize optimization methods on in Euclidean spaces to Riemannian manifolds. How do we do it? Well, it's easy. Namely unconstrained optimization problems like the gradient descent method, Newton method, and the FGS method, if you have heard of it, can be generalized to Riemannian manifolds by just replacing the update formula. So you have addition normally with the so-called Riemannian exponential map. Yeah, so unconstrained optimization methods can be generalized to the Riemannian setting. For example, if we have a function, a scalar function defined on the sphere here, yeah, the sphere is compact, so it has a minimum. It has a minimum and also a maximum. And if we want to search for the minimum, then we start with an arbitrary point, and then we search for a direction which along which the cost function will reduce. And then we go along this direction. But normally we can just do the addition. So we go along the tangent plane. But if we are on a Riemannian manifold, we have to use the so-called Riemannian exponential mapping. So we would like to go along the surface of the sphere or along the manifold, and not only along the tangent plane. Okay, so that's the general idea. And now the thing is, we work with shape optimization. And in this case, why does it not work? Okay, so in this case, what is the choice of space? So it's not a sphere. What is the choice of space and metric in the context of shape optimization? So to get a feeling again, so we would so one point on the sphere here corresponds to some specific shape that we want to have. Okay, good. So and for that we consider the so-called safe manifold of smooth embeddings. So we consider in my presentation here shapes that are obtained by deformations of some initial shape M, or smooth deformations. And we assume that the shapes are embedded submanifolds of the ambient space. And if we do these assumptions, then we can define the so-called shape configuration space. So you have to look here at the EMB of Mn. So M should be a manifold, a finite dimensional one. N is the ambient space. So for example, R2 or R3. Yeah. And EMB of Mn is the set of all embeddings of the manifold M in N. Okay. And because we want to identify two, I mean, if we have, for example, a surface in three-dimensional space, then there are different kind of ways to parameterize the surface. Yeah. If we want to ignore that the parameterization, so if we are only interested in the space in the space of shapes, then we would like to factor out the parameterization. Yeah. And this is done by considering the quotient space or the orbit space. Or so we divide the space of embeddings from M to N with the so-called diffeomorphism group of M, or the set of all reparameterizations of the surface of the shape, and then we get the so-called shape configurations. Yeah, and then the manifold of admissible shapes is then just given by the images of the initial shape under an element of the shape configurations. Okay, that's the idea. And the difference to the example I gave to you in the previous slide with the sphere, this is not a finite dimensional manifold anymore. Yeah? In fact, this is an infinite dimensional quotient manifold. Yeah. So analysis is a little bit harder than in finite dimensional manifolds. And also by assuming these 2 points here, we also consider shapes. I mean, we have an initial shape, and we are interested in shapes that are topologically and also diffeologically equivalent to the initial shape we have. So if the initial shape has one hole, then the set of spaces contains contains shapes that also have one hole. Okay, for example. And again, by dividing here by the diffeomorphism group, this formulation here is independent from parameterization. So to get a feeling, for example, if the initial shape is a circle, yeah, so this is M, and the ambient space is the plane R2, then we consider, by this formulation, we can also consider the boundary of the shape. So we are not interested in the interior of the shape. And now configurations that are admissible, that are allowed, are then those that can be obtained by smooth deformations of the circle, like this. This would be an admissible shape. This would not be an admissible shape because this is not an embedding, but only an immersion. So we exclude shapes like this and only consider those that can be obtained by smooth deformations. For example, if this is our current shape, as you can see in the picture before, so at every point or at every space, there's a tangent space, yeah, around the shape manifold. And in this case, for the surface of the sphere, the tangent space is the plane tangent to the sphere. What is the tangent space in the context of shape optimization or shapes? Well, this is the set of all vector fields on the boundary of the shape that are normal to the boundary. Okay, so this would be the tangent space of the shape of this particular shape. And again, we want to have a Riemannian manifold, so we want to endow an inner product on every tangent space. And a particular example which I choose for this presentation is the so-called Sobolev type Riemannian metric, which is just, but if we have two normal vector fields, two different ones defined on the boundary of the shape here, then we can just take the point-wise inner product of the vector field And I will explain later, this is not enough to define a well-behaved Riemannian matrix. So we have to add some regularization term, which is this Sobolev term here, namely a constant C positive times this inner product, again pointwise, of the weak derivative of the normal factor field defined on the boundary. Okay, so this is the Riemannian matrix which we will use today. Of course, there are many more, but I don't have enough time to explain those. So maybe to get the mathematical, I forgot this one. So again, this is the example of shapes in two-dimensional space, so on the plane. But what I would like to consider today are shells, so two-dimensional surfaces in two-dimensional space. And in this case, this would be an example of shell configuration. So we have the surface, and the tangent space to it is just this, the set of all vector fields normal to the surface. I think it's fairly intuitive. Okay. Any questions over here? Okay, good. So this slide here is a bit technical, so maybe I will just go through it a bit faster, because it's not really important. But if you are interested in the mathematics, again, so the manifold of mappings, or the C infinity, so the function space of the space of functions of that are smooth from M to N can be seen as an infinite dimensional manifold if M is a compact finite dimensional manifold. Especially this is the so-called Fréchet manifold, that is an infinite dimensional manifold modeled on something called a Fréchet space. If you have never heard of it, this is a generalization of a Hilbert space and also of a Banach space. Yeah, so a Hilbert space has an inner product, Banach space has a norm, Fréchet space has a family of semi-norms. So this is more general than Banach or Hilbert space. And the tangent space usually is given by the this is by the I mean, if you're coming from differential geometry, you can just see it as the set of vector fields on the manifold with values in the tangent space of the ambient space, so or the space of sections. But again, this is quite technical, you don't have to remember it. Important is the set of embeddings, again, is an open submanifold of this manifold of mappings, and again, and the diffeomorphism group is an open submanifold of this space here, and also a so-called regular Lie group with Lie algebra of this space of sections. And because of the structure here, we can define well, the quotient manifold, which is called the shape manifold here. So this is a quotient manifold, and also the base space of a so-called principal fiber bundle. A lot of words, you don't have to remember it. Just if you're interested about the mathematical structure that we have here, I have given this slide here. Okay, important is the fact, if you are familiar with finite dimensional manifolds, is many known properties of manifolds do not hold in the infinite dimensional case. For example, if you are familiar with the Hofgreener theorem, this does not hold anymore in the infinite dimensional case. Okay, and also in finite dimensional manifolds, we have only one type of Riemannian matrix. In the infinite dimensional case, we distinguish between so-called weak and strong Riemannian matrix. Strong Riemannian matrix are where manifolds where the Riemannian matrix induces the same topology as the original manifold topology, while the weak ones do not. Okay? In finite dimensional space, all Riemannian matrices are strong Riemannian matrix, yeah, and the only strong Riemannian matrices are so-called Hilbert manifolds. But in the infinite dimensional case, it does not have to be that the Riemannian matrix induces the same topology, and we will especially look at such inner products or such Riemannian matrix, weak Riemannian matrix. Okay, and again, on shaped manifolds, the usual L2 matrix leads to so-called vanishing geodesic distance. What does it mean? I provided you here with the Sobolev type Riemannian matrix. If we choose C equal to 0, so if we do not add this regularization term, then this Riemannian metric induces a so-called vanishing geodesic distance, which means that it can be that two shapes are different, yeah, but the distance according to this Riemannian metric between those two different shapes are equal to 0, and that is not something which we want to have. Yeah? So a distance function should not be 0 if the shapes are different. Yeah, and this is the case. This is an infinite dimensional phenomenon, and it occurs if we omit this regularization term. But if we add it, then it becomes a metric space, and we can do analysis on it. Okay, again, this is quite technical. You don't have to remember it. What is important is now this one. So what we want to do is a gradient-based optimization method. So we start with some initial shape, and then as in usual optimization, we can search for, we can differentiate it, yeah, and we can compute the gradient of it, and then we can move along the gradient with gradient-based methods. Or if you want to have second-order methods, you can do a Newton method or quasi-Newton methods, whatever you want. So how can we do it in the context of PDE constraint shape optimization? Well, we compute this shape derivative. So there's something called the shape derivative of the reduced cost functional. So this is J is again the cost functional, and the reduced cost functional just maps the sine omega to J of omega and U omega, where U omega is a solution to the PDE or a solution to the state equation. And we do it using the so-called shape differential calculus. So you know, every space, every shape has a tangent space, yeah. And there's something called Fréchet derivative and also WAKTU derivatives. Those are generalizations of total differentiation and also directional differentiation on general topological vector spaces. Yeah, and to do it efficiently, we use something called the adjoint state method. So maybe some of you doing optimization have heard of the adjoint state method. I will explain it if you want to, but let's continue. So an example is if we have a volume integral. So if our objective function is the integral of some function f, then an example of the shape derivative of this along some element of the tangent space delta omega is given by the following expression. Okay. And the thing is, this is only the derivative. If we want to do gradient-based optimization method, we have to compute the so-called Riemannian shape gradient of the cost functional. That is the element, nabla e of omega in the tangent space of our shape, which satisfies the following equation here. So this element here multiplied by any direction delta omega should be equal to the derivative of the reduced cost functional along the same direction. And then if we have computed the shape gradient, we can perform iterative descent algorithm based on this gradient information. Okay, so this is the general idea what we can do with this. The only difference is, again, we consider the so-called shape derivatives instead of usual derivatives. Okay, good. Any questions about the optimization framework? If not, I will tell you a little bit about isogeometric analysis. So again, we are working with cells. Yeah. So if we have a two-dimensional surface in three-dimensional space, then the standard finite element method, we would subdivide this surface here into a mesh of triangles. Yeah. And the difficulty is that if you are familiar, if we look at the cell equations, then the usual displacement formulation requires so-called H2 conforming elements. So what this means is that the functions defined on the surface here should be twice weakly differentiable, yeah, which implies that the whole function space here should also include continuously differentiable functions. And if you are familiar with the theory of finite element methods, constructing globally continuously differentiable finite element spaces is not an easy task. Yeah? So there's something called the Argyris elements, which requires 21 degrees of freedom per element, and also the Bell element, which is a further development, requires also 18 elements per triangle. And you can imagine if we have 18 degrees of freedom per triangle, and if we subdivide the surface in a lot of triangles, then we need really a large amount of variables to compute the solution to the PDE numerically. Yeah, that's why it leads. So there are various methods for solving cell equations without using globally C1 conforming elements. And one of the examples, or one approach to solve this problem here, is to use again isogeometric analysis of shells, which means that we use B-splines, yeah, and NURBS patches to both parameterize the shell geometry, so the surface, and we also use the same shape functions or refinements of it to construct finite element approximations of the solution to our partial differential equation. Yeah, and the advantage of using isogeometric analysis is that if we have a patch, or if we have a NURBS representation of our geometry, we can refine it in such a way that the global smoothness, that this C1 condition here, is preserved. So that's the motivation why I use isogeometric analysis. And yeah, this is just a short overview again about B-splines and NURBS. So B-splines and NURBS can be defined. So if we are given a knot vector, then we can define B-splines using the so-called Cox-de Boer formula. So if we are from numerical mathematics, and the difference between the isogeometric approach and the normal finite elements is that we do not use nodal basis functions. So if we look at this function here, so the degrees of freedom describe also the positions of the points here in space. This is not longer the case if we are using B-splines and NURBS. Instead of nodal basis functions, we use so-called control points. Yeah, this can also be weighted. Yeah, if we weight the control points, we get something called NURBS, or non-uniform rational B-splines. So those are just B-splines where each control point is also weighted with some value. Okay. And if this is in one-dimensional case, if we want to consider surfaces or volumes, then we can use tensor products to generalize it. Yeah. Good. And again, there are three kinds of refinement methods that we can do for B-splines and NURBS. We can insert knots. This is the equivalent of H refinement in finite element method. We can raise the order. We can raise the order of the polynomials. This is called P refinement or order elevation. But there's also something which is only present in isogeometric analysis that is called the K refinement, which corresponds to first raising the order of the polynomial, then subdividing the knot into more subdivisions. Okay, and again, this is just a short explanation. An elaborate treatment of NURBS with numerical algorithms can be found in the so-called NURBS book. Okay, so again, some pictures. If this is our initial basis function, which are quadratic B-splines with the following knot vector, then we can do H refinement. Then it would look like this. Or we can do P refinement, we raise the order of the polynomials, or K refinement would look like this. Yeah. In 2 dimensions, the shape functions would look like this on the top right. Okay, and we use these shape functions to approximate. So we use linear combinations of the shape functions to construct numerical solutions to the PDE. Okay, so what is isogeometric shape optimization? Well, here in this case here, we want to consider an initial shape which can be exactly represented by a NURBS geometry. For example, this surface here can be described by the following 8 control points. Okay. And the usual way to do it, or the way that is common in industry and also in the community of IGA, is to just consider the coordinates of the control points. So, the control points here are just points in 3-dimensional space. And then we just consider the control points here as independent design variables in finite dimensional Euclidean space. And then we just put it into a general purpose optimization method. And then we get some solution. Okay. That is the common way or the usual way to do isogeometric shape optimization, or also called the first discretize, then optimize. What I would like to do is not this. So, I would not like to work in usual Euclidean space. What I would like to do is to employ the optimization in the infinite dimensional setting. So we do not just consider these points here as independent variables, but we also want to take information about the structure of the shape manifold into our optimization method. Okay, and in this first optimize then discretize approach, we only discretize when numerical evaluations are required, and we are also allowed to do refinements of this initial geometry. Okay, I hope the idea is clear. And yeah, now the general approach is how do we do isogeometric finite element discretization? So how do we solve PDE on such a NURBS geometry? Well, first of all, there are separate measures and finite element spaces for the optimization and simulation. So, for example, we can have a coarse discretization for the optimization, and then we can refine it to get finer shape functions for the finite element method. Or we can also okay, the important point is optimization and simulation is kind of separated. Yeah, so we will not have to representation for the model and the simulation. And the idea of isogeometric finite element optimization, finite element discretization, is we transform the PDE posed on the NURBS patches to fixed parameter domain, so which is called omega hat, and then we use NURBS shape functions that result from refinements of the NURBS geometry. So this is the NURBS geometry, and we refine it to get a lot more of shape functions. And we do it to discretize the trial and test functions on the parameter domain. So if you are familiar with the finite element method, we can do something called the Galerkin projection. Yeah, and this is similar to standard finite element. So if you are not familiar with it, we can talk in the discussion session. And the thing about this is the convergence analysis now works similarly to usual finite element method. So there are no additional work involved. For example, if we want to compute the gradient, yeah, so in the discrete case, then we can assume that the gradient can be written as a finite linear combination of the shape functions. So these are the coefficients Si, and the shape functions are Ni. Yeah, and then if we want to compute the gradient of it, we just put it into the equation defining the gradient. And what we get is a linear linear equation system here, with the matrix consisting of the inner product of the shape functions of each shape functions and the coefficients Si, which we want to compute. And the right-hand side of the linear equation system is just given by the shape derivative along the shape function Nj. Okay, so we have just A times S is equal to B. Yeah, again, a linear system. And if we solve it, we get the coefficients of our gradient. And again, here we have the inner product of Ni and Nj. And in general, we just use Gaussian quadrature to evaluate these integrals here on each element numerically. So there are a lot of softwares for IGA, for isogeometric analysis, for example, GeoPDEs in MATLAB. This is the software which I use. A more common one is called Gizmo, or Geometry and Simulation Modules, written in C++. And there's also a module, PET IGA for PET-C, if you want to do IGA on the computer. Good. So how much time do I have? Still okay?
Yeah.
Okay. So again, this is a fairly short part. I would like to talk a little bit about the model I use to describe thin cells. So we are talking about thin cells. Before it was about optimization and isogeometric analysis. Now we come to the topic of thin cells. Again, we have the following three cell kinematic assumptions. So we represent a shell again by its mid-surface and assume the following three hypotheses. So the Mintlin hypothesis says that straight line segments normal to the mid-surface depicted in red should vary linearly and also remain straight after deformation. So if we deform it, it should also remain straight and not be wiggly or something like that. Okay. The second one is the Kirchhoff hypothesis. Straight line segments normal to the mid-surface should also remain orthogonal to the mid-surface after deformation. Here you see this dashed line here is normal to the mid-surface, and after deformation, it should also stay orthogonal to the mid-surface. Yeah. And the third one is inextensibility. The thickness does not change during deformation. So the length of this dashed line here should also stay the same. These are the three cell kinematic assumptions that I make for this presentation. And using these three assumptions, we can represent shell by the following parameterization, which is also called an inextensible one-directed Pascasarjana surface. And the set of geometric functions that we have is then given by the following set here, which is just the set of all parameterizations which can be written in the following way, where omega is parameterization, gamma is the parameterization of the mid-surface, nu is the so-called director vector, and zeta is just the variable in the z direction, in the how do you call it, not transversal direction. And usually nu is just the normal, the vector normal to the mid-surface. Okay, so this is just a picture again. So here we have the parameter domain. This is our shell, and this is a configuration of the shell, which is described by the deformation phi. So, and the idea is we start with three-dimensional elasticity. To get the shell equations, we start with three-dimensional elasticity. Yeah. And the three-dimensional elasticity follows from a lot of balance laws. Yeah, maybe you have heard it from continuum mechanics. So we have the conservation of mass, we have a conservation of momentum, conservation of angular momentum, and also conservation of energy. From these four balance laws, we can, in the stationary case, we can derive the so-called boundary value problem of elastostatics, which looks like this in material picture. So instead of the normal Cauchy stress tensor, we have the so-called first Euler-Kirchhoff stress tensor. And on the bound, we can subdivide the boundary into two parts: the Dirichlet boundary and also the Neumann boundary. On the Dirichlet boundary, we just say that our solid body does not deform. And on the Neumann boundary, we say that there's some kind of traction force acting on the body from the outside. Okay. And then we consider the following configuration space and space of variations. And if you are familiar with partial differential equations, this is the strong formulation of our PDE. And we can, by multiplying with an element of the space of variations, we can transform it into a so-called weak variational formulation, which looks like this. S is now the second Euler-Kirchhoff stress tensor. E is the strain tensor, or the E dash. E prime is the derivative of it, and also called the rate of change deformation tensor, I guess. And on the right-hand side, we have the body forces, that's EXT. So the forces that act on the body on the inside, and also the traction forces GEXT that acts on the Neumann boundary. Okay. We can also write it in a general form, namely we have a bilinear form, A of omega, which depends on phi, and eta should be equal to the right-hand side, which is abbreviated to B omega of eta. Okay, so this is our weak variational formulation for three-dimensional elasticity. And the idea is now in three-dimensional elasticity, if we have so-called hyperelastic isothermic material, we can also characterize the solution to the boundary value problem here as the minimum of the so-called energy functional, which is given here by the principle of Piet-Wellworth. So A phi eta is equal to B eta if and only if it is a stationary point of the energy functional. So you can look at this weak Pascasarjana formulation, or you can look at it as the Euler-Lagrange equations, while this is the corresponding Lagrangian. So if you are talking in physics. And the idea now is we derive the equation for the shell we derive the equations for shells by using this characterization. So we use the same energy functional, but we now express the strain tensor in terms of kinematic variables of only the mid-surface. Yeah. In this sense, the strain tensor can be written. This is usually defined as this term here. Now it can be written as something which only depends on membrane strain and stresses. Yeah. And also the bending part. So if you have a shell, you have deformations like this, and also deformations like this. And we just separate those two kind of deformations, and then we integrate the strain energy to the thickness to get the so-called effective stress resultants. This is just the membrane stresses, and this is the bending stresses or bending forces, I guess. So, and in the end, what we obtain is a weak formulation for thin elastic shells. So we just differentiate the energy functional, and then we get the following expression. Okay. The problem now here is that this still depends linearly on eta, on the space of variations, but this is not now non-linear in phi. And we can still solve it by using Newton's method. But to make things easier, to simplify, we just linearize the strain tensor around the undeformed configuration to obtain the so-called linearized Koita or Kirchhoff-Loff shell, which is given here below. So these are the linearized versions of the stresses and the strains. This is again the right-hand side consisting of body forces and also surface forces. And in the end, what we get is the following shell energy functional, which we use for our PDE. Okay, good. So now some numerical examples. This is about thin cells. To get some feeling, maybe pictures are better, I guess, than words. So first, to simplify, we do not consider PDE constraint state optimization problem. So we leave out the PDEs first to get a feeling and look only at shape optimization. So for example, the isoparametric problem, maybe some of you have heard of it. Among all simple closed curve in the plane with some fixed perimeter, we want to maximize the area of the enclosed region. So this is our problem. And now the question is, we want to fix the perimeter, and then we want to vary the shape such that the area is maximized. What, in your opinion, what would be the solution to this problem? Or you can, this is a classical result from calculus of variations. What is the shape with a fixed perimeter that maximizes the area? Is it a square? Is it a triangle? What do you think? Any ideas? Yeah. So it should be a convex shape, because if you look at this, this is not a convex shape. We can draw a line from this point here to this point, and then we can flip this part here such that the perimeter stays fixed, but the area increases. Okay, so it should be a convex shape. And if we do it iteratively, or if we do calculus of variations, the solution is just a circle with the same parameter. Okay, that would be the solution to this problem. And I have used my numerical method to solve this problem here. So I start with the initial design of the square, and after 17 iterations, I guess, if I'm not mistaken, I discretize this again with using NURBS and B-splines, so using isogeometric shape optimization. And after 17 iterations of the gradient descent method, with backtracking line search, with Amir rule and such, I would get the following shape of final design, yeah, which is again a circle with the same parameter as the initial design. These are the iterations again. So 7 iterations. So it starts like this, and then it moves the control points in such a way that where we get something like this. And then after 7 iterations, we get something which looks like this. And this is also an advantage of isogeometric shape optimization. So if you imagine, if we subdivide this into triangles like usual finite element methods, we would not get smooth boundaries. Yeah. If we subdivide it into triangles or quads, and then we just move the nodes around, we would not get something as beautiful as the circle here. So this is an advantage of using isogeometric analysis, because we can represent shapes that are smooth like this. Okay, good. Another kind of example which is also interesting is the so-called minimal surface problem. For example, these also occurs if you play around with soap bubbles and soap films. So we want to minimize the area of a cylindrical surface here bounded by 2 circles. Yeah, and the solution is not a cylinder, but this is something which is called a catenoid. Yeah, this is a catenoid, or a surface of revolution of something called the catenary. So maybe you're also familiar with the concept. If you have a string, and if you hold the string with 2 fingers, and then the shape that it will form is a so-called catenary, and a catenoid would be the surface of revolution of this catenary. Okay, and I also applied my method here to this problem, and I start with the following initial design, and after some iterations, we get the shape of final design, which looks like this. Okay, I can also show it in a simulation in live if you want to. So I opened. Wait, where is it? I cannot go outside this. No, wait a bit. So, okay, so this simulation written in MATLAB using GeoPDEs. And here, if we let it run, so I hope you can see it. So this is the initial design, and then using the optimization method, after some iterations, it will also convert to the catenoid, which looks like this. A very simple problem to check whether my method works or not. Okay, good. I think it still computes until now. Okay, it's done now, and this is the shape of final design for the simple problem of minimizing the surface area of a surface bounded by 2 circles. And if we now return to the presentation, so this is the result. Now we want to consider optimization problems with some PDE constraints, especially the compliance minimization under fixed area constraints. So the compliance is just defined as the energy, as the strain energy here. So 1/2 of the bilinear form FU and U. The PDE we consider is again the shell equations, which I told you before. And we use the following function space here. This is the space of twice weekly differentiable function H with 0 boundary conditions on the Tehnische boundary, and under the constraint that the area stays fixed. Okay, and again, our surface is an element of the shape manifold I told you before in the beginning, and U is an element of the state space here, which again depends on the shape gamma. So this is fortunately, as in the linear case, a so-called self-adjoint optimization problem. So we don't have to compute the we don't have to compute the solution to the adjoint equation. And a difference is that to compute the shape derivative, we have also considered the so-called transport equation for cells. So maybe you have heard of Reynolds transport theorem, and it does not hold. It only holds if our subset has the same dimension as the ambient space. For cells, we have a 2-dimensional surface lying in 3-dimensional space, so we have to alter the transport equation a bit. Again, we use steepest descent and backtracking line search with Amio rule, and we use a penalty method to incorporate the equality constraint on the geometry. So this constraint on the area we handle using a penalty method, and Okay, and this part is, I think, not really important. If I can talk about it later, but this okay, maybe I can explain it a bit. So on computing the Riemannian exponential mapping, for example, on the sphere is easy because we have an analytical expression for it. Yeah, for the geodesic on the sphere. But usually it's not easy to compute the geodesic solution to the geodesic equation. So instead we consider so-called retractions or approximations to the solution to the geodesic equation. For example, on the sphere we we move along the tangent plane and then we just project it onto the sphere. That would be a retraction. It's not the geodesic, it's not the Riemannian exponential mapping, but it's an approximation of the geodesic, which is sufficient if we do a gradient descent method. And let's look at the time. Okay, I still have some time. Yeah, well, another example is the plate with hole problem. This is also a shell, but we constrain it onto a plane. So if we look at the equation here, we ignore the bending part here, the SBEB, we ignore it, and we just look at the membrane part. So this corresponds to usual linear elasticity in 2 dimensions. And our problem is we want to minimize the compliance again of this linear elastic plate with a hole subject to some forces outside. Yeah, so like this. Because this is symmetric, we just consider one part of it with the following boundary conditions. And now we consider this line here as our variable boundary, and everything else should be fixed. And in this case, well, if we apply the method, then the iterations would look like this, and the analytical solution is given by a circle. So yeah, or a Carter circle in this case. And after 8 iterations, we see that it is close to the analytical solution of the problem. We can also look at age refinement. So something like here we only use 2 control points, but the idea is we can refine it. We can use more control points. If we use more control points, then we see that the values, the objective value tends to some value. So it shows a behavior of convergence experimentally. And also if we raise the order of the polynomials, or so-called P refinement, it shows similar behavior to H refinement. Yeah. And now we're coming to the last example. This is the half cylindrical shell under static mechanical load. So before we have only a plate constrained to a plane. Now we look at the full problem, namely we have a 2-dimensional surface lying in 3-dimensional space. And in this case, our initial design is a half cylindrical shell, which looks like this. We fix it on the left side, and then we have a roller support on the right side. So if we push down with gravity or with our hand, then it will deform like this. Okay, and we have homogeneous gravitational boundary force, and the thickness be 0.1, corresponding to the coordinate system here. We use the following material parameters. Okay? And now the question is, how can we deform this initial design here such that if we push down, such that the deformation is minimal, yeah. So such that it is rigid and not like this. Okay. What do you have any idea? What could we do with the shape? Yeah. So there are many ways to do it, but if I run my simulation now, what we obtain is something like this. Yeah? So we have here first a low resolution final design with 4 times 2 elements, which looks like this. For the medium resolution, it looks like this. And for high resolution, maybe 16 times 8 elements, it looks like this. And the thing I have to remark is the final design depends highly on the chosen optimization parameters. So if we alter it a little bit, then we would get a slightly different kind of problem. Especially we have a formation of wrinkles if we discretize it finer and finer. And it leads to the question, is the problem well posed? Is there an optimal solution to this problem? Because if you look at this, if we add wrinkles over and over again, we would get a structure which is intuitively more rigid than a structure without wrinkles. So maybe mathematically this problem here is not quite well posed as opposed to the plate with hole problem. Okay, but from a practical point of view, if we discretize up until some degree, then we can view. I mean, from a practical point of view, if you are an engineer and you want to design some shape, then we do not have to consider the fine resolution. We can just use the coarse one, because this already reduces the objective function. Okay, and here some comparisons with other methods. This is the FDTO approach. So if we just consider the control points as design variables and we do optimization in Rn, then we would get something like this. It requires 34 iterations until it stops, and the objective function is given by 0.11. If we use something called the symbolic preconditioning, which corresponds to computing the gradient instead of using the derivative, we get something which is better with 20 iterations and 0.04. But if we consider the Riemannian structure of our shape optimization problem, then we get this solution here in less iterations with a slightly better optimization value. Objective value. Here I just use steepest descent in all cases, but I also want to compare it with FMINCON in MATLAB. So I just did it for the FDTO approach. If we use FMINCON, then it requires 15 iterations until it reaches this point here, and then it kind of do not change for 40 or so iterations. But here also in this case we see that considering the Riemannian structure is important in gaining this result here. So okay, that's it, I guess. So summary and outlook. What have we done today? So we have considered the so-called isogeometric shape optimization using the so-called Riemannian framework, where we consider the set of all embeddings of a surface in three-dimensional space that are diffeomorphic to some initial space, say as a Riemannian manifold, and we perform optimization using the Riemannian gradient. Yeah. And we have also talked a little bit about the model for thin elastic shells that I use for this presentation. And then I also gave some classical examples using the isoparametric problem, and also the minimal surface problem, and also the compliance minimization of structure, thin cell structure under fixed area constraint. And some things we could talk about again. I have chosen a specific Riemannian metric, but if you look in the literature, there are a lot of different kind of metrics you can put on the shape space, but I only use one, so we can further discuss this if you want to. I'm currently working with multi-patch geometries with kinks. So here, this is a one-patch structure. It can be described by one nerve patch, but I'm also interested in more complex geometries where we can put multiple patches together. So this is something which what I'm working on. And then I also did not talk about the incorporation of nerve wakes. This is something which I have done in my master's thesis. If you are interested, we can also talk more about it. And the kind of geometric constraints that I considered are just something like, oh, I want to fix the perimeter, I want to fix the area. So maybe it's also interesting to consider other types of geometric constraints, like, oh, I don't want this here to intersect some kind of other objects in the space, for example. So, and again, I have done steepest descent using the Riemannian gradient. This is fairly a simple optimization method. So maybe we can do more sophisticated ones like Newton or quasi-Newton methods. And again, about the wrinkle formation, I have to analyze mathematically whether the problem is well posed or not. Yeah. So because intuitively we can just add a lot of wrinkles to make the object more rigid. So there is an infimum of the compliance, but I'm not sure whether a minimum exists. And again, I talk about the linearized Coit-Kirchhoff cells, but you can also extend it to so-called Geissner-Mindlin cell model, which is, for example, also used to describe the surface of the Earth, for example. So we can the surface of the Earth or the lithosphere can also be modeled as a thin cell. Good. So that's it from my side. I hope this is useful for you all. Here are the references that I used during the whole presentation. Thank you for your attention. And yeah, that's it.
Thank you very much for your nice talk, Rozan. So please, is there any questions from the audience? Most of them are the master and doctoral students.
Yes.
I think this will give you some insight, more knowledge, and inspiration. I do. I feel inspired with your talk.
Thank you very much.
Yeah.
Yep.
Before I give you a question, so please.
So you can also ask in Indonesian if you want to.
Ya. Ini bahkan saya tuh bawa suasana karena tadi mendengarkan bahasa Inggris, jadi kita berbicara. Sebetulnya tidak harus berbahasa Inggris. Jangan, oh ya, Bu Helena, oke. Dari para mulai 3 nih ada Almira. Ayo, satu lagi kemarin saya mengundang mahasiswa Pascasarjana baru. Ada. Oh, yang online juga boleh. Wah, Bu Budi sudah live. Oke, jangan salah dengan yang online dong. Maka mungkin sebelum Bu Helena, saya berikan kesempatan dulu kembali kepada Prof. Budi untuk memberikan pertanyaan atau komentar. Maka Prof. Budi, ini Kang Rozan jauh-jauh dari Kaiserslautern. Silakan Bu. Oke,
Terima kasih Ibu Kaprodi. Saya lihat tadi ada review ya.
Ini Prof. Budi dari kediaman beliau.
Ya, kita.
Ya, ini dengan Assalamualaikum warahmatullahi wabarakatuh, Bapak Ibu, para mahasiswa dan pemateri. Saya panggilnya apa ya? Ini anak saya ya, atau cucu mungkin. Saya campur-campur ya. Masih tiasa bahasa Sunda,
Bisa paham, tapi kalau ngobrol agak sulit.
Okay, Pak Rozan ya. So I'm very proud of you ya, because you have followed the study abroad and then you can share a very nice presentation. Although it's part from my topic in statistical aspect ya. But I think that I hope if you don't mind, not question more in subject, but maybe if you don't mind, would you like to share experience with the student in mathematics, postgraduate mathematics in Bandung, ya, in Unpad? For example, how maybe to push ya, or to get strong motivation, ya. Kang Rozan ya, mungkin bagaimana tuh memotivasi kan tinggal di luar negeri jauh dari orang tua tapi bisa sukses gitu ya. Nah, ini untuk teman-teman supaya lebih semangat begitu. And the second is about the what kind of a collaboration between university or maybe department in your university ya, with industry. Yeah, so for example, we have a collaboration, and then we can try to use the model that, or we can try to give a model with the relationship with the problem in industry. Thank you, sukses selalu ya.
Terima kasih. Oke, jadi dalam bahasa, ya.
Boleh bahasa Indonesia ya,
Iya,
Bu ya?
juga nggak apa-apa kan.
Ya,
Jadi yang pertama itu intinya bagaimana bisa
Survive gitu ya.
Survive
Jauh
tadi
jauh dari orang tua, bagaimana ya?
Ya, cerita aja.
Mungkin bedanya itu saya kan di Jerman udah dari kecil juga gitu ya. Ke sana itu pertama kali kelas 4 SD. Jadi mungkin agak beda gitu dengan orang lain yang pertama kali kalau kuliah di sana gitu. Jadi buat saya ya Jerman itu udah kayak
Lembur.
udah kayak rumah sendiri. Jadi mungkin agak beda dan pengalamannya beda dengan orang lain yang baru S1 atau S2 atau S3 ke Jerman kayak gitu.
Lahirnya di Jerman dulu.
Enggak, lahirnya di sini.
Oh,
Di Jerman waktu itu 2016 9 tahun umurnya. Ya, jadi gimana ya?
Motivasinya itu jadi kan kalau di sini maaf ya, ini teman-teman yang S2 S3 harus bermotivasi tinggi, tapi harus didorong gitu ya. Nah, di sana kan apalagi sendirian, nah, ya orang tua Pak Yudi kan waktu itu udah pulang.
Iya.
Gimana?
Ya, intinya kalau bekerja dengan ya hal seperti ini itu topik yang kita pilih itu, hal yang kita lakukan itu harus benar-benar hal yang kita sukai gitu ya. Jangan memaksakan diri untuk melakukan riset atau sesuatu yang kita sendiri tidak antusias gitu, lebihnya. Iya.
Tipsnya katanya ya pilih topik yang disukai. Jadi kalau udah suka dengan topiknya ya.
Iya, biasanya
lebih asik ya.
Lebih
Jadi
asik.
temannya itu adalah betul sekali itu dulu saya juga sempat merasa seperti itu. Jadi kalau sudah asik dengan topik yang kita kerjakan gitu ya, bahkan ada grafik sendiri ya, jadi tidak kesepian lagi ya.
Iya.
Jadi teman kita itu adalah pekerjaan kita. Betul ya?
Iya.
Gitu. Itu katanya tips yang bisa dipertahankan. Mungkin Bapak Ibu akan teteh di sini ya yang sedang menempuh S2 dan S3, cintailah topiknya ya.
Iya.
Betul kan? Mungkin yang sudah merasakan kemarin berjuang perspektifnya kan dikejar deadline gitu ya. Jadi sudah ya, kamu fokus ke topiknya. Itu ya mungkin ya.
Iya.
Kemudian lagi dari Pak Budi yang selanjutnya mungkin mengenai
Tadi dengan ini Budi ya, kolaborasi bagaimana di sana?
Ya, kolaborasi dengan industri. Jadi mungkin ini Kang Rozan di Indonesia sekarang ini kan sedang digaungkan FMIPA ya. Jadi kebebasan belajar ya. Kemudian kampus merdeka. Kemudian ini sudah mulai ditularkan untuk prodi S2 S3. Kami juga kemarin pada prodi diundang oleh Keluarga 1 ya Bu ya mengenai MBKM ini. Artinya harus ada extend gitu ya. Riset itu terkait erat dengan kolaborasi langsung dengan industri seperti itu. Nah mungkin bisa share di sini gitu ya pengalamannya, apakah bagaimana caranya ataupun kolaborasi apa saja mungkin dari departemen matematik di sana ya.
Jadi kalau di spesial di Kaiserslautern itu, jadi Universitas Kaiserslautern itu bekerja sama dengan yang namanya Institut Fraunhofer, yaitu institut lebih negeri yang bekerja di bidang industri gitu. Jadi ada kaitan erat itu antara Universitas Kaiserslautern itu dengan Institut Fraunhofer. Dan jadi banyaknya juga banyak kerjasama gitu ya antara institusi itu sama universitas, dan jadi Kaiserslautern memang terkenal gitu sebagai industrial mathematics itu yang ada mulai terkenal gitu di Kaiserslautern karena kerjasama dua itu. Maaf tadi pertanyaannya detailnya apa gitu? Jadi apa?
Boleh Bu diulang Bu.
Jadi tentang kolaborasi apa maksudnya?
Ya, jadi kan kalau misalnya tadi ya Rozan itu mengambil topik gitu kan, optimization, agreement-nya. Nah, apakah itu tuh terkait juga karena ada kerjasama industrinya gitu?
Kalau yang ini saya lakukan independen dari industri, tapi misalnya di Fraunhofer Institute itu ada juga yang lagi bekerja dengan additive manufacturing gitu. Jadi mencari bentuk optimal untuk tekstil dan sebagainya, itu dilakukan juga di Institut Fraunhofer gitu. Kalau untuk yang saya lakukan sekarang ini independen, tapi ya bisa dilihat aplikasinya juga bisa banyak gitu kan, karena kalau udah selesai gitu mungkin kita bisa gunakan ini untuk mengoptimisasikan misalnya bentuk dari mobil atau bentuk dari kendaraan lainnya yang terdiri dari cangkang tipis gitu ya.
Baik, terima kasih banyak. Sukses ya.
Udah mau Prof Budi berangkat sana.
Boleh menambah?
Oh silakan Prof. Boleh mau menambahkan ya Prof Budi?
Ini ya Prof Budi ya, ini bagus sekali.
Terima kasih Prof Budi.
Ya, bisa mengambil pelajaran ya di sana.
Karena Kaiserslautern itu sebenarnya besarnya di matematik.
Ya.
Jadi di Kaiserslautern kita di sana ya ada beberapa institut yang salah satu yang terbesar itu ITWM, itu Institut Matematika Teknik dan Ekonomi.
Industri dan ekonomi.
Ya, nah itu salah satu yang besar di Jerman dan itu juga didukung oleh Fraunhofer Institute tadi. Jadi kalau kan ada mahasiswa di sini suka pakai MP3 ya, itu lagu format itu dari Fraunhofer Institute. Matematik itu Bu.
Ya.
Ya. Kemudian mungkin yang di komputer itu ada semacam namanya Fraunhofer File System. Itu untuk penyimpanan data paralel. Itu juga dari Fraunhofer Institute. Jadi matematika sangat besar di sana. Kemudian ada dua ya, satu Fraunhofer Institute, kemudian satu lagi Felix Klein. Ya kan?
Felix Klein itu lebihnya kerjasama antara Fraunhofer sama.
Ya, nah itu juga satu institut dan kemudian kebetulan Rozan juga dulu backup beasiswanya dari Felix Klein kan ya.
Iya.
Ya, itu memang ada ini Bu, institut matematik itu sangat besar. Dan yang terakhir itu yang software engineer.
Ada Max Planck.
Max Planck ya. Max Planck Institute juga itu semuanya di matematik Bu. Jadi kalau di Kaiserslautern sebenarnya yang besarnya matematik.
Terima kasih Prof. Yudi. Ya soalnya begini tambahkan ya, kalau kami kan ada Himpunan Matematika Indonesia. Terakhir itu kan kami mengusulkan di Simposium Matematika itu tahun 2021. Bagaimana kalau kita bisa nggak membangun institut untuk matematik itu gitu ya. Tapi sampai hari ini juga belum ada balasan. Ada kita kan punyanya LIPI ya, Pak Yudi adanya LIPI dulu ya. Sekarang BRIN semua ya, BRIN kan?
Ya. Pada Kaiserslautern kita pernah punya MOU. Prof. Budi waktu Prof. Budi ya dulu.
Ya, FMIPA. Masih lanjut kan harus?
Dilanjutkan Bu, karena di sana kan PIC-nya pensiun. PIC-nya pensiun, kemudian kalau dari matematik ada link ke sana bisa dibangunkan lagi.
Iya, Bu, jadi diperpanjang aja. Sayang itu kan bisa untuk komunikasi juga, kolaborasi. Terima kasih Prof. Yudi. Ini soalnya ya, Swanten AA tuh sama dengan ayahnya suaranya.
Terima kasih Prof. Yudi atas pertanyaannya juga ya.
Ini kepada Pak Yudi. Pertama saya akan selamat dan saya datang ke sini, yang kedua mungkin selamat spesial selamat kepada orang tua kamu, Profesor. Prof. Yudi sudah bisa memberikan fasilitasi. Nah kalau di Indonesia kan sekarang yang sedang sibuk itu di bidang pendidikan itu yang namanya pentahelik ya. Pentahelik ya, jadi government, industry, kemudian ya, higher education dan seterusnya. Nah sebetulnya itu masih jauh kita kalau kita melihat ke sana. Tapi yang dilihat di METU yang misal ya Middle East Technological University di Ankara Turki itu sudah bagus. Trihelik malahnya. Ya, bukan pentahelik lagi tapi trihelik ya. Jadi maka dengan tiga itu sudah government, industri, higher education ya. Itu sudah bagus ya. Jadi karena seperti pabrik karpet itu mereka sudah tidak memikirkan lagi tentang penelitian bagaimana pengembangan karpet, tentang motif, material itu sudah enggak, itu diserahkan ke perguruan tinggi. Kemudian masalah peraturan-peraturan itu di government ya. Nah, di kita belum. Nah ini mudah-mudahan nanti dengan Rozan ini untuk matematik bisa memfasilitasi ke sana. Pak Yudi lah, Pak Yudi ya. Ini kita trihelik aja udah bagus ya. Dengan trihelik aja sudah bagus. Dan ini saya sampaikan kepada para mahasiswa, ya calon-calon mahasiswa pasca matematika ini. Ya pertama ini presentasi sangat clear ya. Mana parameter, mana vektor, mana konstannya itu jelas ya. Jadi jangan sampai nanti kalau nanti ada sidang saya uji, jangan sampai ada yang salah lagi, parameter ditulis vektor ya. Jadi coba dilihat presentasi yang sangat clear ya. Jadi terima kasih dan ini sudah cukup clear. Jadi ini cukup bisa memfasilitasi ya teman-teman mahasiswa pasca di matematik 4 ya. Dan ini yang kita lihat ini jelas dari sistem ini adalah ini yang kita sebut nanti ya, ini adalah optimization analysis ya, optimization analysis ya. Jadi yang di S3 itu ada mata kuliah riset operasi analisis kan. Nah ini salah satu materinya adalah optimization analysis seperti ini, bukan lagi applied ya. Applied itu waktu saya kuliah itu udah nggak dianggap, tapi ya analytical optimization ya seperti ini ya. Analytical optimization itu aja mungkin komen saya. Terima kasih.
Terima kasih Pak Sudrajat.
Jadi terima kasih.
Tadi saya kembali memberikan kesempatan. Oh ya tadi Bu Herna. Oke, bagus ya. Silakan. Boleh perkenalkan diri kemudian
Nama saya Dr. Winata di pertanyaan ini.
Ya.
Maaf kalau misalkan saya
Enggak apa-apa ya.
ke depan.
Supaya dekat dengan mikrofon.
Oh, dengan mikrofon biar di rumah bisa dengar.
Oke, saya ulangi, nama saya Bagus Robi Meganta dari Master.
Baru lulus nih Pak.
Jadi maaf bila saya salah. Jadi tadi dari yang disajikan presentasinya hanya membahas satu bahan baku gitu. Betul kan, Pak?
Ya, jadi kita melihat framework optimisasi dengan cara Riemannian itu ya.
Nah, ya, andai kan kalau misalkan saya punya suatu bentuk cangkang yang bisa saja terdiri dari beberapa bahan gitu. Misal yang pertama bahannya A, kemudian bahannya B, apakah
bisa?
Nah,
Bisa dibahas ya. Tidak masalah, tapi di software yang saya tulis sendiri ini belum ada implementasi seperti itu. Tapi misalnya di komunitas IGA IGA itu sudah sering dilakukan. Jadi kita material itu nggak harus homogen gitu, bisa juga berbeda-beda ya.
Menarik ya.
Ya.
Bagus. Ini juga bidangnya interpretasi dan optimisasi. Kemarin risetnya mengenai online transportation. Publikasinya baru diterima di
ya.
Kalian promosi.
sama izin bertanya juga, kebetulan saya sekarang ada tertarik di riset mengenai sepatu khusus untuk perawat gitu.
Ya.
Nah, jadi kan untuk sepatu itu sebenarnya ada tumpukan-tumpukan yang lapisan-lapisan yang ada sol dan lain-lainnya.
Ya.
Berarti untuk memodelkan tersebut kita memodelkannya tetap sama membuat cangkang tipis. Tapi untuk tadi tuh yang bahasa fisika itu lupa namanya yang 0,7 itu
0,7
Nah itu yang tadi yang nah yang ketika kita tekan berarti kita perlu menjumlahkan dari tekanan yang bisa diterima oleh sol dan bahan lainnya.
Ya, itu tergantung dari model yang digunakan. Jadi ada juga beberapa orang yang menggunakan tadi katanya cangkang berlapis. Itu di engineering application itu banyak dilakukan juga gitu. Jadi intinya kita memodelkannya sebagai cangkang yang dihubungkan lagi dengan persamaan lain gitu. Jadi intinya persamaan cangkang, tapi bukan hanya sekali, tapi beberapa kali gitu untuk memodelkan lapisannya.
Ya, jelas. Pertanyaan terakhir. Secara umum ini dikenal sebagai permasalahan apa ya?
Yang mana ini?
Ya, yang saya sebutkan barusan. Jadi untuk literatur lebih lanjut.
Oke, tadi permasalahannya itu kan soal sepatu. Terus tugasnya apa? Jadi maksudnya permasalahannya apa? Apa yang mau pengen optimisasi atau?
Ya, optimisasi cangkang sepatunya.
Bentuk sepatu.
Ya, bentuk sepatu dan agar dapat nyaman juga.
Ya itu.
Maksudnya lebih ke bagaimana literasi apa yang perlu saya perkuat.
Itu lebihnya kan ada literasi juga ya. Untuk awal yang penting itu di sini nggak ada. Ya ini kan itu shape optimization. Jadi yang pengen di optimisasi itu kan bentuk dari sepatunya, kan? Jadi ya itu termasuk shape optimization.
Tapi udah optimal control problem kayak gitu pernah
dengar.
ya.
Iya,
Jadi itu basicnya di situ. Gitu. Jadi kalau mau ya belajar dulu optimal control problem, terutama optimization with partial differential equation. Gitu. Tergantung kalau ada PDE atau enggaknya gitu di permasalahan. Kalau mau saya bisa berikan juga nanti beberapa literatur kalau tertarik. Ya,
Terima kasih banyak.
Ya, sama-sama.
Terima kasih Bu.
Baik, selanjutnya ada lagi pertanyaan. Saya yang pengen tanya ya, karena saya mau bertanya tahan tidak nanya. Boleh. Yang lain ada
Ya, nggak apa-apa. Yes. Yes.
Mungkin saya belum familiar
F-Mincon itu mengandung beberapa metode, bukan hanya satu aja gitu. Yang biasa dipakai itu interior point method, tapi bisa disetting juga jadi SQP, sequential quadratic programming. Terus ada apa lagi di sana? Ada beberapa gitu, bukan hanya satu. F-Mincon iya. So,
and then you suggest use another deterministic method like Newton and Newton.
Quasi-Newton method, ya.
Are there any difficulties to use the because you suggest another deterministic?
So the question is why don't we? Okay, so the problem with Newton is it's a second order method. So we have to compute not only the gradient, but also the Hessian of the problem. And computing the Hessian is a bit more involved than computing the gradient, especially there's something called the shape Hessian. You can compute it, but it's a lot of work. So that's why I do not use Newton methods. Quasi-Newton methods can be used, so it only requires the gradient. The problem is this is for unconstrained shape optimization problems. So if you have some constraint on the problem, then it's better to use SQP or interior point methods.
Yeah.
I want to ask some opinion. Are you mind to apply any maybe methodologistic method?
Sorry, can you speak up a little bit? Or
Maybe how about your opinion about using another maybe
meta-heuristics?
Or another
Stochastic gradient or something like that. Yeah, this is a good idea. So I haven't done it before, but using stochastic gradient methods, especially in the context of shape optimization, might be really good, fruitful, because I told you the results I got, they highly depend on the optimization parameters I choose, and they also highly depend on the initial shape I choose. So if you want to get a better understanding of the shape space and the shapes that are close to the local minima, then it's perhaps better to use meta-heuristic methods. Yes, but I haven't done it for my work now.
Thank you so much.
No problem.
Mungkin kalau boleh ikut menambahkan sedikit ya. Tadi benar seperti yang disampaikan Pak Sugeng, ya bahwa ini adalah analisis untuk optimisasi. Kemudian saya mengikuti awal, ini memang sebetulnya Bu ini kita perlu mengklasifikasi dulu jenis fungsi gitu ya. Tadi kan sudah dijelaskan ya bahwa syarat perlu dan cukupnya tentunya mungkin harus membunuh, dan karena kan ini kita kerjanya dengan PDE ya, harus diturunkan dan lain-lain. Nanti klasifikasi dari fungsi-fungsinya itu bisa kita deteksi ya, apakah kita harus juga menggunakan genetic algorithm, kalau tidak cukup ini juga sudah sangat powerful gitu menurut saya ya, kalau lihat presentasi tadi. Kemudian kalau saya dari Pascasarjana ya, kemudian kenapa di menggunakan Newton misalnya, itu biasanya ada di percepatan melalui menurut saya computational capability ya, dan algoritma pencarian solusi. Jadi mungkin kita sebelum memutuskan ya, saya harus pakai metode atau tidak, kita harus analisis dulu variabelnya, apa yang terlibat, fungsinya, apa yang terlibat, sama ini strong suggestion-nya dengan metode ya. Jadi kita nggak asal, oh ini masalah ini kayaknya bisa deh pakai metode kita analisis dulu gitu ya, itu yang saya tahu jadi mungkin menambahkan.
Terima kasih.
Oke, yang lain, ini banyak yang berkaitan dengan optimisasi, kemudian mungkin setahu saya sih dari beberapa aplikasi yang dilakukan oleh teman-teman kami itu sudah mulai juga banyak yang mengajar ke arah optimisasi juga ya. Jadi mungkin topik pembahasannya bisa sebagai masalah kemudian matematikanya, tapi mungkin seperti saya dengan Prof. Budi juga ya, sekarang sudah mulai optimisasi di semi-parallelogram seperti itu. Jadi yang kita gunakan misalnya linear programming saja, tapi masalahnya gitu ya, ini tadi harus berkaitan dengan ini. Nah kalau misalnya saya juga boleh bertanya, ini tidak ada bertanya ya. Mungkin kalau untuk saya pribadi ya, ini seperti kuliahnya juga harus lebih nostalgic gitu ya untuk saya, karena sebetulnya kuliah optimisasi atau kuliah OR itu seperti ini, yaitu tadi yang disinggung sama Prof. tadi. Isinya analisis semua, isinya aljabar semua gitu ya. Nah, sementara kalau di sisi kita banyak juga mungkin para mahasiswa seperti memberikan garis pedas gitu ya antara matematika murni dengan matematika transformasi. Nah, sehingga ini memberikan wawasan yang sangat bagus gitu ya untuk membuka wawasan bahwa sebelum kita melakukan eksperimen menghitung sesuatu, sebetulnya kita harus ungkap dulu story behind atau karakter dari masalah kita dengan fungsi-fungsi dengan misalnya sifat-sifat matematis ya. Nah kemudian kalau yang untuk saya pribadi yang kedua ini juga memberikan inspirasi yang sangat kuat gitu ya. Selama ini setelah melakukan banyak riset kami banyak bekerja dengan menyelesaikan masalah industri ya, misalnya dari keuntungan ya, kemarin sudah cerita juga sama COVID ya, dari keuntungan menghitung cost gitu ya, minimalis resiko ya, di keuangan, di investasi online dan masalah yang saya kerjakan. Tapi di sini ini memberikan inspirasi yang sangat kuat gitu ya, bahwa kita juga bisa melakukan apa-apa saja yang ada di sekitar kita. Gitu kan, tadi kan cangkang tipis itu kan bisa kita gunakan di banyak hal gitu ya. Jadi mungkin contohnya pembukaan mobil misalnya, atau tadi dari Robi ya, bagus sekali ternyata bikin sepatu gitu ya, itu juga permukaan tipis, kemudian harus dioptimisasi juga gitu. Sehingga harga sepatu bisa mahal ya, bisa beda-beda harganya ya gitu kan. Betul ya, tentu kalau mereknya ini gitu bisa sekian gitu, padahal namanya sama ya. Banyak juga yang KW-nya kan gitu ya. Nah ini buat saya gitu ya, ini sangat menginspirasi. Kemudian ini juga ya kembali ke OPDE tadi, kekuatan dari persamaan diferensial gitu ya. Di sini sudah banyak berkaitan bukan hanya variabel tapi juga harus melibatkan waktu. Kita bicaranya bukan x-nya, variabelnya bukan x saja, tapi x-t gitu kan. Kalau x-t kan berarti harus berkaitan dengan waktu. Jadi juga teknik kalkulus ya, fungsional analisis ini sangat kuat di sini ya. Integralnya mungkin sebelumnya kita ingat integral atau kalkulus aja gitu ya. Saya juga udah jarang pakai kalkulus integral gitu ya, tapi ini memberikan inspirasi yang sangat kuat. Kemudian tadi mungkin dari sisi optimization methodnya juga banyak disebutkan sesuatu yang sudah banyak dikenal, tapi mungkin di mahasiswa kami belum begitu dalam penggunaannya gitu ya. Misalnya tadi kan Dimensional Methods ya. Kemudian mungkin mahasiswa saya bimbingan dengan saya ini sebetulnya sudah mulai saya dorong untuk mengungkap geometri gitu ya, geometri dari daerah visible. Ya, misalnya kayak apa ya ini ada saya dia sudah bekerja dengan robust optimisasi dengan polyhedral uncertainty. Nah, bagaimana polyhedral itu tadi itu juga ya, itu bentuk geometri yang kita ungkap, analisisnya juga sama. Ya. Kami bekerja juga dengan ellipsoidal uncertainty, gitu ya. Ini juga mereka harus bisa mengungkap bagaimana ellipsoidal itu adalah transformasi linear dari bola. Ya. Nah, ini mungkin dimengerti wawasannya dari rekan-rekan yang di rumah. Ada yang mau bertanya lagi, silakan kaitkan dulu supaya kamu bisa lihat. Mangga, Kang Fadli mau tanya. Serius banget nih Kang Fadli, ayo mau nanya?
Belum.
Boleh? Belum? Baik, yang di ruangan ini saya mau ingin bertanya. Ya. Baik, tampaknya sudah cukup. Nanti barangkali kalau kamu ingin melanjutkan di sini, boleh ya kontak lewat emailnya gitu ya, kepada Kang Rozan, nanti kita mungkin bisa berdiskusi lebih lanjut lagi. Dan ini juga ya mengingat waktu ya. Kemarin kata Prof. Yudi, aduh, sama yang 45 menit, nggak kan ya, 45 menit kurang gitu ya. Baik, barangkali sudah kembalikan ke Ibu Elina, selaku presentasi. Terima kasih atas perhatiannya.
Terima kasih atas pemaparan speakernya ya, Rozan, juga pada audiens kalian. Mungkin kita akan masuk ke sesi pengenalan sertifikat oleh guru Kadep, boleh makannya kepada sekaligus ke dokumentasi.
Ya, mangga.
Saya
Ada Kang.
Enggak, ini Rozan yang memberikan satu sertifikat penghargaan. Ucapan terima kasih atas sharingnya. Semoga banyak memberikan bagi banyak pihak dan kita lanjutkan kolaborasi.
terima kasih.
Banyak ya wartawan.
Terima kasih.
Ya, masuk tangan, Pak. Masuk website Unpad, nanti saya buatkan tulisan.
Baik, mungkin demikian kita tutup acara Tirsa Lecture Series ini. Mudah-mudahan Mas Rozan bisa mengisi di kegiatan berikutnya ya di depan dengan matematika. Terima kasih banyak di audiens yang datang. Mungkin itu saja. Mohon maaf apabila ada hal-hal yang kurang berkenan. Mungkin kita foto.
Baik, untuk sesi akhir, mohon berkenan Bapak Ibu yang di rumah, saya akan stop sesi.
Bisa tambah sedikit boleh lima aja. Dan ini sampai Oktober pertengahan ada di
Oktober. Oh iya. Barangkali ada kegiatan nanti.
Ya Pak.
Apa aja?
Diumumkan itu besok sekalian.
Oh iya. Mohon juga barangkali kami dari Prodi menyampaikan besok juga kami ada satu lagi guest lecture. Jadi kebetulan ini kita punya alumni ya, Bu ya. Alumni ya, Pak ya. Alumni Pascasarjana dari Melbourne ya. Akan memberikan topik mengenai the role of mathematician in supporting international business. Jadi mohon kehadiran Kang Teteh yang hadir. Mangga besok di ruang MC pukul 14 ya. Nanti pengumumannya setelah ini. Kan mohon kehadirannya. Saya juga tadi sudah menugaskan beberapa orang masih ada ya. Mangga sebelum kita tutup kami persilakan Prof. Sudajar, Prof. Yudi, Bu Emma, Bu Helena untuk maju ke depan untuk berfoto dengan Kang Rozan. Mangga, saya kira ada kali lagi. Ya, enggak, ayo kita foto sama-sama yuk. Semuanya. Semuanya jadi betul sedikit gitu ya. Yang ini boleh di depan. Yang cowok. Semoga yang mudahan bermanfaat ya Bapak Ibu yang di rumah juga. Enggak, bisa aja sih. Nanti gantian ya asalnya ya.
Gini aja, Bu. Nggak apa-apa. Kan udah
Iya, ini kan 1, 2, 3. 1, 2, 3. Katanya mau gantian katanya. Saya mau Mariza gantian.
Kalau apa begitu? Bisa jadi bagian.
1, 2, 3.
Kayaknya belum.
Mohon. Bapak Ibu yang di rumah, terima kasih ya atas kehadirannya. Baik, mohon izin untuk
Daftar reguler aja.